Although baking seems like quite an ordinary task, it's possible because of many complex chemical reactions. Today, I happen to be making some bread, so let's delve into the chemistry behind this age-old food. As for ingredients, here's what I'm using to make simple homemade bread. Yeast, water, flour, salt, beer, and vinegar. That's it. I'm sure many of you have these ingredients lying around in your house, but when combined together, many incredible reactions occur. To start off, let's talk about yeast. Yeast is a living, single-cellular eukaryotic organism, a fungus. Today, you can buy yeast dried. Dried yeast became readily available during World War II, and then activate it yourself by adding warm water. It is one of the most important ingredients in bread, as it creates the light, fluffy, airy insides of the dough. Since yeast is living, it goes through cellular respiration, consuming sugars and outputting carbon dioxide. This process is known as fermentation. To go a bit more into the reaction itself, we start off with a simple glucose molecule. Fermentation for a glucose molecule is often called glycolysis, which literally means the breaking down of glucose. Glycolysis is not unique just to bread making. It happens in our cells every day to create the ATP needed to survive. Within the yeast cell, there are multiple different enzymes that are called zymes that help catalyze glycolysis. Initially, the enzymes transform glucose into pyruvic acid. For an organism, the pyruvic acid is usually used to make ATP. But for bread making, we're most concerned with other products of the reaction, which include carbon dioxide and ethanol. The production of ATP requires oxygen, which is why we need oxygen to survive. So we create an anaerobic or oxygen-less environment for the yeast in bread. Without oxygen, the yeast enzymes take the pyruvic acid and transform it into CO2 and ethanol. The carbon dioxide bubbles are what cause bread dough to rise and give a final product a nice, airy texture. The ethanol gives bread a unique flavor. Note that this fermentation process is not used solely for bread, but for many alcohols as well, where yeast is modified to produce more ethanol and less carbon dioxide, and this is why we used beer to make our bread. Yeast is known as a leavening agent, or an ingredient that produces gas to help dough rise, but it is not the only leavening agent used in baking. Although yeast is common for bread, you might have used leavening agents such as baking powder or baking soda for other baked goods like cake. Baking powder and baking soda also produce CO2. Baking soda is the common name for sodium bicarbonate, which is a base. It reacts with acid in your recipe to create nice carbon dioxide bubbles. Baking powder contains both baking soda and a dried acid, so when you hydrate it, it produces carbon dioxide as well. Although yeast is very important, it would never have any purpose if not for the flour in making bread. Flour provides the carbohydrates, or glucose, for the yeast to consume. However, flour is a complex mixture and also contains a wheat protein called gluten. While yeast gives bread its airiness, flour, and specifically gluten, gives bread its structure. Gluten is a mixture of two different proteins, gliadin and glutenin. When gliadin and glutenin mix together with water, they form gluten. And as a refresher, we all know from studying macromolecules that proteins are polymers of amino acids, connected to each other by peptide bonds, which is also why proteins are often called polypeptides. Shown here is the polypeptide synthesis through dehydration. The different sequences of the 20 amino acids create different types of proteins. This sequence is called the primary structure of the protein. This primary structure dictates the secondary and tertiary structures, or the three-dimensional shape of the protein. Gliadin and glutenin have very different shapes, as gliadin is super tightly coiled, and glutenin is a longer, loosely coiled strand. In terms of bread, gliadin allows dough to be stretchy, and glutenin ensures strength and elasticity. Glutenin and gliadin form a gluten matrix in the dough, giving some structure and support so the bread doesn't completely collapse. This woven structure isn't very strong, which is why kneading is an important part of the bread-making process. Kneading the dough pushes together the gliadin, glutenin, and water into a definite structure of strong, orderly sheets of gluten. However, over-kneading the bread can also be detrimental to the final product, as it allows a lot of oxidation. Before kneading, bread also needs time to rest, which allows yeast to produce carbon dioxide bubbles, but it also strengthens the gluten structure. Adding flour and water, which contain the ingredients for forming gluten, together and letting it sit is called autolysis. During autolysis, the straight sheets of gluten produced by kneading are not yet formed, but enzymes called proteases go around to the disorganized strands of gluten and cut them up into smaller protein segments. These smaller bits of protein make it easier to form an organized gluten sheet during the kneading. Water plays an important role in baking bread, as it allows gliadin and glutenin to form gluten. With more water, the gluten becomes more extensible. Extra water can also make bubbles in the bread. When it bakes, the water turns into steam and creates little hollow pockets. The amount of water is extremely important, and many bakers focus on the hydration content of their dough. By America's Test Kitchen, the optimal hydration content for bread is 68%. Note that everything up to this point has been while the dough is still raw. Adding heat and baking the dough into bread involves a whole other host of chemical processes, a few of which I will outline. The first reaction is called a Maillard reaction, which begins to occur at 285 degrees Fahrenheit. Different reactions begin to occur at different temperatures, as you'll see. In short, Maillard reactions are reactions between proteins or amino acids and sugars. These reactions cause foods to brown, release smell, and produce flavor. And they're not only found in breads, but in really any food that has protein and sugar, which includes meat. Because a Maillard reaction causes browning, it is often referred to by chemists as non-enzymatic browning, because it only involves amino acids making new bonds with carbohydrates. The specific molecules formed depend on the temperature of the reaction and the type of amino acids and carbohydrates present. The most common bread compound produced by the Maillard reaction is 6-acetyl-1,2,3,4-tetrahydropyridine, called ATHP for short, and causes bread to have its distinct bready smell. The reaction starts off by adding heat to sugars. These sugars will be oxidized and create what are called open-chain or reducing sugars. These compounds contain a characteristic carbonyl group or carbon double bonded to an oxygen. The amino acids will then bond to this molecule on the open carbon end. From this reaction, we get a rather unstable and weak compound in the bread. The carbon and nitrogen much prefer to be double bonded to each other, so the molecule goes through dehydration and loses a water molecule to form a double bond. The products are therefore water and what we call an N-substituted glycosylamine. The name literally means a sugar protein. However, we are not quite done. The open-chain nature of the glycosylamine arrangement is not stable and must go through a special process called an Amadori rearrangement. Through the Amadori rearrangement, we get a new compound called a ketosamine, where the carbon and nitrogen have a single bond, but the carbon and oxygen share a double bond. From these ketosamines, there might form other smaller compounds like fission products or reductones, but we won't concern ourselves with these complex reactions today. The big takeaway from this is that Maillard reactions involve amino acids and sugars and are responsible for the taste, smell, and browned appearance in many foods. The next reaction is similar to the Maillard reaction, and you've probably heard of it before: caramelization. Caramelization, like the Maillard reaction, is another type of non-enzymatic browning. Unlike the Maillard reaction, however, caramelization involves only sugars, not sugars and proteins. Caramelization is quite famous for producing nice, sweet, nutty flavors in caramel, naturally. However, it can also apply to different foods like vegetables, and in our case, bread. The mixture of Maillard reactions and caramelization is what makes bread taste so delicious. Caramelization refers to the oxidations of sugars and removal of water via steam, and occurs at different temperatures depending on the type of sugar, but somewhere within the range of 230 to 320 degrees Fahrenheit. Sucrose, glucose, and galactose all caramelize at 320 degrees Fahrenheit, while fructose caramelizes at 230 degrees Fahrenheit. Products made with high fructose corn syrup, therefore, produce a lot of reacting sugars and often have a more brown appearance. Initially, the reaction starts with sucrose, which, while under heat, breaks into glucose and fructose. Sucrose, a common table sugar, is a disaccharide, or a molecule made from two smaller sugars, monosaccharides. Fructose and glucose then decompose even further to smaller, volatile aroma compounds. In caramelization, there are a couple common aroma compounds: furans, diacetyl, maltol, and ethyl acetate. They smell nutty, buttery, toasty, and fruity, respectively. The next step in the reaction is called the oligomerization of fructose and glucose, which seems like quite a scary name in a process that makes caramel. An oligomer is like a polymer, but has a set number of joined compounds, not an infinite one. The fructose and glucose join together through dehydration. The water is released as steam and form three-ring sugars. For example, two fructose molecules can come together and form difructose dianhydride. Simply, the smaller sugars react to form larger ones. Right now, chemists aren't quite sure what the exact reaction mechanisms are, but the final products of this oligomerization of fructose and glucose are caramellan, and caramelin, a complex chemical reaction to make such a simple sweet treat. The last reaction I will mention is pyrolysis. Pyrolysis is the term that is used to describe when foods are overheated. The name pyrolysis can be explained by two parts. Pyro means heat, and lysis means breaking down. You might also hear pyrolysis referred to as thermal cracking, thermolysis, or depolymerization. In cooking, pyrolysis can be a good thing, as it breaks down big molecules into smaller ones and makes food easier to digest. However, over 355 degrees Fahrenheit, too much pyrolysis can cause charring, which is both not very tasty and also possibly carcinogenic. When molecules are heated, they vibrate, and with intensely high temperatures, they vibrate quite a bit. so much so that they stretch and break. Pyrolysis often refers not to cooking, but to the production of biofuels, which I suppose is similar, just the heating of organic matter. So I hope today you learned not just about baking bread, but also the incredible amounts of science behind everyday products. So the next time you pick up a loaf, just think about how much chemistry went into making it.